So this next video is devoted to the extra problem, where you have here this situation. You have an ideal spring, ideal rope, ideal pulley, no frictions anywhere. Mass 2 is larger than mass 1. The spring has a certain an unstretched length L2. So this will be L2 here. This is L2 if it's unstretched. But this mass is heavier, so it tries to pull this mass up, so the spring stretches a little bit. And the question is, how high above the ground, Y0, will mass M1 be? The pulley is ideal, and the moment of inertia about the center of mass is 1/2 the mass of the pulley, r squared. The mass of the pulley is just symbolized by little m. This mass is M2 and this one is M1. And how high above the ground will it be? Well, since there is no motion, we in a moment we'll pull this one down, and then as you can imagine, it will start going up and down. It will start oscillating. It goes like that. The spring stretches more, comes back, stretches more, comes back. We're going to do that in a moment. But for now, it's at rest. So if it's at rest, it means the net force is 0, and the net torques are also 0, because the pulley is not accelerating this way nor this way. We will call here the tension 1, and this tension here is 2. And so we will have the following. On M1, for M1, the forces on it are the force of tension T1, and then the spring, since it's stretched, the spring will pull it down, the force from the spring, the force of the spring. And remember, the force of the spring is down, but it has a magnitude of K times the amount by which you stretch it. The amount by which you stretch it is, if this is Y0, then you have stretched it by Y0 minus L0. That's by how much you have stretched it. So it's equal to K in magnitude. I know it's downward, so it will be negative K because it's downward. I'm sorry, not L0, Y0 minus L0. That's that. And then there is the force of gravity, which is M1G. So these two forces are equal. It means T1 minus the force of the spring minus M1G equal to 0. So T1 will equal to these two added together. So I would get T1 will equal to M1G plus K Y0 minus L0, right? All of them were on the other side. The M1G was negative M1G, and this was negative K Y0 minus L0. We moved them equal to 0, and we moved them to the other side. So we get this here. Get this. This is a little longer problem, more challenging. And on the M2, we have, here is M2. We will have, there are two forces on it, right? The M2, it's there is gravity pulling it down, and there is the mass of the spring. I'm sorry, just the tension going up. And the tension there, we can call it T2. And this is M2 times G. And the conclusion here is that T2 is simply equal to M2G. T2 minus M2G equal to 0, so T2 equals to that. For the pulley, we have two torques on the pulley. There is T1 this way, and T2 this way. And that torque is T1R, that's counterclockwise torque, that's positive, and clockwise would be negative. So T1R minus T2R equals to 0. That means T1R equals to T2R. So T1 equals to T2. So we get T1 is equal to T times 2. So that concludes that T1 equals to T2. So we can set these equal to each other, and we can find out what Y0 is. So we will equate this to that. So we get M1G plus K times Y0 minus L0, that has to equal to M2G. M2 times G. And so move that to the other side, so you get K Y0 minus L0 will equal to M2 minus M1 times G. When you move it and factor the G out. M2 divide both sides by k, and move the L0 to the other side. So you get y0 equal to L0 plus g over k, and then m2 minus m1. And I hope that corresponds to what I have here in the solution. So I have m2 minus m1. Yeah, that looks good. All right. We will look now at part 2 of this problem. So we're going to move block 1 with respect to the equilibrium. All right, so we're going to, let me draw what's going on for part B. So for part 2. For part 2, it's the same problem. We're going to move M2 down a little bit, so this will rise, and then we will let go. So here's what happens. Here's our pulley. And here is 1. Here is the spring. Spring is here. Here is 2. And the position of 2 is y2. And the position from the ground to M1 is y1. And the pulley is either spinning this way or this way. Right? So it would be going like that. They're oscillating like this, and the pulley spins with them. And so the question is, what is the kinetic energy of this system as they oscillate? Well, the kinetic energy is M1 would have a kinetic energy 1/2 mv squared, and M2 would have a velocity would have a kinetic energy of 1/2 mv2 squared, and the pulley would have a kinetic energy of 1/2 I omega squared. So let me write it here for part 2. Right, so you have a pulley spinning, it has kinetic energy. We're not talking about potential energies yet. So part 2. So for this whole system, I'm running out of chalk. Let me get something a little longer than this. So the kinetic energy of the system is K, and it will have the kinetic energy of the first mass plus the kinetic energy of the second mass plus the kinetic energy of the pulley. Pulley has rotational, and these have translational kinetic energies. So that's equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 I omega squared. Now, y1, v1 will equal to the derivative of the position vector to mass 1, dy1 dt, right? Remember, y1 measures the position from here to here. And if mass 1 has a positive velocity, mass 2 would have negative velocity, and if mass 1 has negative velocity, mass 2 would have positive velocity, and the magnitudes of those velocities are equal. If this one rises by 1 inch, this has to drop by 1 inch because the rope has the same length. And the pulley has to turn accordingly. So we'll figure that out also. And V2 will equal to dy2 dt, and that's equal to negative dy1 dt, which is equal to negative v1. So I'm going to write that as negative v1 here. And the pulley, remember, omega is our theta, but the tangential velocity will equal to r times omega. So in magnitude, v1 will equal to r omega. R times omega. I put positive there, like that. So omega squared, in other words, will equal to v1 over r, the whole thing, squared. So let's plug here. So we get the kinetic energy, therefore, will be 1/2 m1 v1 squared plus 1/2 m2, but v2 is v1. v2 is negative v1, but when you square it, it just becomes v1 squared. And then here I have 1/2. The moment of inertia was given to us over there, about the center of mass, it's 1/2 mr squared. So 1/2, the moment of inertia, which is 1/2 mr squared, and omega squared, but omega is v1 over r, the whole thing squared. So v1 squared over r squared. So a couple good things happen. So we have the r squared cancels. We have a v1 everywhere, and we have a 1/2 everywhere. So I'm going to have k will equal to 1/2. The 1/2 will be pulled out, and the v1 will be pulled out. So I'll pull it out, put it on the other side. So I have 1/2 m1 plus m2 plus this 1/2 is pulled out, but we have this 1/2 left. So 1/2 little m, and then the r cancels, so I have v1 squared. So that's the kinetic energy. I'm going to just double check I did not make any algebraic mistakes. And it looks okay. It looks okay to me. Yeah, it looks fine. Okay, so now the second, for part 3, they want us to take the time derivative of this kinetic energy. We want to take the time derivative of this kinetic energy, dk dt, all right? So we just take the time derivative. You would see for a reason. It's oscillating, and we want to find omega for it. If you go directly to Newton's laws, it might be a little tougher, but this way it's a different way, and I think you will like it. Part 3. Find dk dt. Well, dk dt. Let's take derivative of this. Constants. Only the v is changing because the v goes up and down, and so the derivative of v squared will be 2v1 and then dv1 dt by the chain rule. So the 2 comes down, so all that remains is this. So I have m1 plus m2 plus 1/2 of little m, and again the 1/2 went away with this derivative. When you take the derivative of v1 squared, you get 2v1, so the 2 cancels, and you just have v1, and then times dv1 dt, which is the acceleration a1, the acceleration of object 1. So that is that. Now let me look at the next part. What they want for the next part is find the time derivative of the gravitational potential energy. So what is the gravitational potential energy? Well, the gravitational potential energy, you have the total gravitational potential energy. You have let me show you the drawing here again. This is above the ground, so it has a gravitational potential energy of mgy1, m1 gy1, right? And this one would have m2 gy2. And then the pulley is above the ground, so it has a mass, it has like mg times the height of the pulley from here all the way here. All the way here. I'll just call it h. This is height h. I'll just call it h. It doesn't matter anyways because we're taking its derivative. And then, so they just want the gravitational potential energy. Part 4, find the u gravitational dt, right? Well, first of all, u gravitational will have m1 gy1 plus m2 gy2 plus the mass of the pulley times gravity times the height of the pulley. Take the derivative. The height of the pulley is not changing with time, so when you take the derivative, this one goes out. It's out. So du g dt will equal to, let's take the derivative. You have m1 g dy1 dt, but that's v1. So m1 g v1, and then plus m2 g v2, m2 g v2, and then that one is 0. But remember, V2 is negative of V1. V2 is negative V1, so I will replace this by negative V1, and so du, let me put a box around this one here, we'll probably need it, G dt, and then this will be M1 G V1 minus M, oh, this should say M2. M2 G V1. Factor the G in V1, so you got M1 minus M2 G V1. That's the time derivative of the gravitational potential energy as a function of time. Okay? Now, let's look at the next question. The next question says, find the time derivative of the spring potential energy. Well, so let's see. Part 5. Du spring dt. Well, let's see. Let's just draw the spring. And here is M1. And let's say here is the natural length of the spring. Here is L0. And so this stretch here, that's will be, this is Y1. So the amount of stretch will be Y1 minus L0, right? This is Y1 minus L0. And we want to take the time derivative of the, the potential energy stored in the spring will be 1/2 K times the amount by which you stretch it squared, which is Y1 minus L0 squared. Okay? If it's on the bottom here, if it's compressed, it means Y1 minus L0 would be negative, it means it's compressed. But when you square it, it's positive anyways. But whatever it is, if Y1 is greater, it will be positive. If Y1 is less, it will be negative. So let's take the time derivative of this. Du spring dt will equal to, the 2 comes down, so you have just K, and then Y1 minus L0. But the chain rule says you have to take the derivative of the inside. This is constant, so its derivative is 0. So this is dy1 dt, which is just V1. So let us put a box around this. All right. Okay. So we will go to the next question. So the next question says, use the fact that, first of all, we know that the total mechanical energy will be the total kinetic energy plus the total gravitational potential energy plus the total elastic energy for the spring. That's the total mechanical energy. Since there is no friction, we know that this has to be constant. So the derivative of E with respect to T has to be 0. So the derivative of kinetic energy with respect to T plus the derivative of gravitational potential energy with respect to T plus the derivative of the potential energy of the spring with respect to T, they all have to add up to 0. Because, let me write it here. dE dt will be d dt of K, kinetic energy, gravitational potential energy, spring potential energy, and this has to be 0. And the derivative of a sum is the sum of the derivatives, so we already calculated these derivatives. All we have to do is add them and set them equal to 0. So this plus this plus this plus this, they have to add up to 0. And they say find an expression as a function of y1 for the acceleration. So use this to find a1 in terms of what? Y1 minus y0. All right, y1 minus y0. So that's what I want to write down. So I'm going to, I have to raise the board, and because the board, I'm running out of board. Let me get my This one, yeah, it's right. It is the one that writes well. So I'm going to just right here. I have dk dt plus du gravitational dt plus du spring dt. They have to add up to 0. So let's write down the dk dt first. dk dt is m1 plus m2 plus 1/2 m v1 a1. So m1 plus m2 plus 1/2 m1. So I have m1 plus m2 plus 1/2 m v1 a1. That's that. Plus this one. Make sure I didn't copy wrong. 1/2 m1 v1a. Yeah, that looks good. And then plus the derivative of this, of the dug dt, that's m1g v1 plus m2g, actually it's right here. It's m1 minus m2g v1. m1 minus m2g is m1 minus m2g v1, I think. It's too short. Yeah, that looks good. And then plus the elastic, plus du spring dt. Du spring dt, what is it? It's k y1 minus L0 times v1. K y1 minus L0 times v1, and the whole thing has to equal to 0. Let's look at it from far away, make sure everything looks good. I think it looks fine to me. So that looks good. Now things are looking simpler. So the velocity will, if the velocity is equal to 0, you just get 0 equals to 0, which is okay, fine. That's called the trivial solution. But I want the velocity to be non-zero, so I could divide by the velocity v1 here. So that cancels. And yeah, I want to get the acceleration now. So I'm going to divide everything by this. So I have, and move it to the other side. So let's divide by this first. So I have the acceleration. When I divide by this, it goes away. And then plus m1 minus m2 divided by m1 plus m2 plus 1/2 of m times g. I divided this by this. And then plus k plus k over m1 plus m2 plus 1/2 of m times y1 minus L0 equals to 0. Let's move everything to the other side. So I get A, acceleration, will equal to. When you move it to the other side, this thing becomes negative, but let me just put m2 minus m1 then, because it's negative m1 minus m2, that's m2 minus m1, it becomes positive, m2 minus m1. And I have m1 plus m2 plus little m, mass 1, mass 2, the mass of the pulley, 1/2 of it, m over 2, g, and then when you move this, it becomes negative, so I have k, and I have m1 plus m2 plus 1/2 of little m, and then times y1 minus L0 equals to, no, not equals to 0. We move them to the other side, so that looks good. Okay. Let me just double check it. Okay, it looks good, so everything is good. But they want it in terms of y1 minus y0. Okay, which is fine. I don't want the L0. So L0, let me write it here. L0 will equal to y0 minus g over k times m2 minus m1. So let's replace L0 by that and see what we get. So we get the acceleration, will equal to m2 minus m1 g divided by, I would just write parentheses here for this whole thing. And then minus k over parentheses. Parentheses means all this stuff is inside. And then here I have y1 minus L0. But L0 is y0 minus this. But so I'm subtracting y1 minus L0, so you flip the sign. So it becomes g over k, and then m2 minus m1. No, it becomes plus because I'm subtracting it, so this becomes plus, and this is the minus y0, like so. And I have the acceleration will equal to, let me write it one more time, m2 minus m1 times g divided by all this stuff on the parentheses, and then minus, let me multiply this one by these and pull it out of the parentheses, so I have k over some stuff here, and then g over k, and then m2 minus m1, like so. And so I multiply this by that, and then plus k over this stuff times y1 minus y0, like so. And notice m2 minus m1 times g over stuff, the k cancels, m2 minus m1 times g over stuff, so this whole thing cancels, and that's a good thing. So we get a1, let's just say a1, 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 a1. So a1 will equal to k over that stuff, k over, let me write that stuff now, so m1 plus m2 plus little m over 2 times y1 minus y2. y1 minus y2. Oh, I'm sorry, minus y0, like so. So I think that looks good. Well, it almost looks good. When I multiply it, I forget the minus sign. This times this, that's the minus sign, but when I multiply this by the y1 minus y0, I forget the minus sign. Yeah, I knew that it has to be a minus sign because otherwise this will grow exponentially, but it should be oscillating. Okay? So now, if we make a change of variables, if we let capital Y or capital Y1 equal to little y1 minus y0. y0 is a constant, so let's take the derivative of this, then dy1 dt will equal to d little y1 dt, and dy1 second derivative with respect to t will equal to the second derivative of y1 dt, which is equal to a1. So I'm going to write here this a1 will equal to negative k divided by m1 plus m2 plus m over 2, and then y1 minus little y2, I'm going to call it again y1, and so you have a1 will equal to negative some constant here, I'm going to call it omega squared y1, and therefore omega squared, or omega itself, would be the square root of k over m1 plus m2 plus little m over 2, and that's the frequency or the angular frequency of small oscillations. Okay, that's the end of this problem. You see, when you had a simple mass on a spring, you have the forces, and it's much simpler. But here, if you go directly by Newton's laws, I think it's this way that usually the energy approach is cleaner and nicer. Even though we are talking about Newton's laws, but not, at least not directly. All right. I will see you in the next chapter, which is about, I think, traveling waves.